Here is the geometry. And I can also introduce quickly how to set up the problem. So if you are not familiar with the product or the simulation platform yet, I will quickly go through. And in case you need some more details, you can also check the previous webinar we had. It's a similar simulation case. Okay, so basically here we have imported the coil geometry, which is here. So you can import step files or build from scratch. And here we have added air around the model using the operations we have available in the editor. But if we check about the materials quickly, I will hide some domains first. So this is the one using Thinshell method. Therefore, we don't have any, if we zoom in a little bit, we only have the cable embedded in steel. And in the formulation, we apply the Thinshell approach on the surface now. So we don't have the volume at all in the model. So we had the airbox, then we have the steel and cable in this Thinshell model. Also, you can add additional surfaces for post-processing if needed. For example, the surfaces for integrating net currents through the winding. As well, here you can introduce the simulation parameters. So we have the transport current, the amplitude of that. We apply a ramp function. And then we have the three conductivities. And once they are defined here, we can sweep over the variable later in the simulation section. So here we have the cable conductivity as 1E12 and steel 1E7. Then in the physics section, we define H-phi formulation. And H is for all the conducting domains. Then phi formulation, the scalar potential is only in air, in non-conducting region. And we constrained the potential to have unique solution. And here, using the cuts, we can introduce net currents to the model. So basically, it goes like this. You only define a loop around the conductor where you want the current to flow. And I want to emphasize that the flexibility of the software. So, for example, let me show this from the phi point of view. We have basically two holes in this modeling domain, which means we need to introduce two cuts to apply currents. And for the non-insulated winding, we even don't know what the current is. But in also, this has been done automatically behind the scenes, so the user only needs to define the current which are known. So you want only to address the current to the cable, and we automatically solve for the currents behind the scenes for the unconstrained. And this is very convenient feature when you are having a really complex shaped geometries such as stellarator. So you don't, in the CAD, you don't need to take care of anything regarding the unconstrained currents. Then in the simulation section, let's make a copy of this old one. So you can see here we have the meshing options, and the mesh looks like as it was in the slides. You can visualize it here, and then we can do a sweep over the conductivity here. And what I forgot to mention, we don't yet have the Thinshell in the GUI available. We will package it after some more testing, but in future you can add it here as you would add electrical insulations or something else. But now we have implemented the Thinshell via scripting interface, and we will do it more convenient for you later. So let's do not go to the details of the formulation. I will just show how to run a sweep over the conductivity. So we can input the Thinshell conductivity here and choose the values we want to run it. And we can also output currents losses by adding them here. So let's run the simulation. We can follow the simulation in the logs, and I can show, before it starts, I can show some parameters here. You can choose your simulation type here, then the solver type, and initialize the time stepping parameters. And we have two options for the solvers. We have direct solver and the iterative. And the iterative one is based on the DDM, the domain decomposition method. And especially when you have nonlinear materials, it can speed up a lot the simulations. So basically, behind the DDM, we split the mesh in pieces and solve all the pieces parallel, and the information is changed only on the surface layers of the sub mesh pieces, and this can scale up the simulation time significantly. Here you choose on how many pieces you divide the problem, and you can choose the node type. If you need more RAM, you can choose a bigger node, or you can just increase the node count. And here I think we have something starting. You can see all the jobs, they start simultaneously, and here you can follow the progress. So you can see we have two cuts, one unconstrained and the one we set the current through. We can see how many unknowns we have, and in this case we can run it with one node. And typically the bigger the problem is, you can increase the node count and see the scaling appearing there in when checking the simulation time. And now we can see the time steps, what it's taking. And we can go to the live plotting and start seeing some results appearing. And the most interesting maybe for this is the ramp up dynamics. So here I'm plotting the magnetic flux density in the bore of the magnet. And we can also add a current there to see. Let's put the bore field on the right axis. So now you can see how does the change in conductivity affect the magnet ramp-up dynamics. Here the dotted line, it's the applied current, and then you can see the colors. The first one color here has the lowest conductivity, and if you follow the curves, you can see it's behaving almost linearly now. So we addressed almost full insulation for the Thinshell. So all the current wants to go to the cable in that case, and you can see almost linear behavior in the magnetic field. Then if we start increasing the conductivity of the Thinshell, the current wants to go during ramp up, it wants to bypass the cable easier. And you can start seeing some slopes there. And the higher the conductivity is, the bigger delay you can see in the magnetic field ramp up time. We can also plot the losses. So, for example, in the cable, and then we can see the losses behaving. First, we have eddy currents appearing, and we ramp up the current in 10 seconds, and then you can see some stabilization in the losses. And this will run up to 30 seconds. After that we can see some field shots from there. You can also investigate the losses in the Thinshell. And again, after we have ramped up the current, you can start seeing decrease in losses because the currents, they are going to the cable. And also here, since in the first case we had almost full insulation due to the bad conductivity of the Thinshell, almost all the current goes directly to the cable and stabilizes there. And in cases you have a higher conductivity in the Thinshell, you see that the current, after current ramp up, the current starts to redistribute inside the winding and wants to go eventually to the cable. So you can see that after current ramp up in these cases with higher conductivity in the thin cell, you can see it. Okay, now it's current is increasing kind of in the cable now. You can see it as in increase in losses as well. And here you can also see that by changing the conductivity of the thin cell, the actual uh, stable conditions are not exactly the same as you would have with uh, fully insulated cable. So there's some currents always bypassing the cable in steady conditions as well. And this is regarding, for example, the stellarator design. With this thin cell method, you can uh, affect uh, how does the magnet dynamics behave, and you can build more accurate models so that you can have even maybe more elements in the cable because you don't need to really mesh the thin volumes. And if you want to consider partially insulated cases, and if you can affect the conductivity between the cable and the steel around, then you can use this thin cell model to check uh, how would it affect the magnet ramp-up dynamics. But I guess we can stop the simulation here, even though it's pretty close already, and we can visualize quickly the uh, magnetic field distribution. Or do we have it available? Not yet, but okay, I ran it before already. So, for example, let's refresh. For example, the current, uh, yes, current distribution. Let's re reload the solution. You can visualize the currents here also in the steel if you like. This is at the final stage, and also, for example, the field magnetic flux density on the cable surface itself. And if you would take the plots during the ramp up, you would see how does the current start distributing inside the steel volume. But basically, this was everything I wanted to show for today, and thank you for listening.